The statement about the midterm and the second quiz was not recorded. So probably I'm going to repeat it again. So we are not going to have a midterm during the typical midterm period, but we are going to have a second quiz after the midterm. So that will be probably either end of October or maybe early November. So continue the theme is that if we have a closed contour, that is clockwise, counterclockwise contour, and if Fz is analytic in D, then this is equal to 0, right? That is so-called Cauchy's integral theorem. Number one, if Fz has a simple pole or pole, so higher order at C naught, then two pi I residue of C naught, right? So we talked about residue. That is when Fc can be combined with Bm C to the m, Bm minus 1, C to the m minus 1, B1, C to the B0, sorry. The residue is B1, right? And this cup is called residue. So the problem is how to calculate the residue. Probably we'll copy paste. Pretty nice, right? So I finally learned how to cut and paste. So in this case, if it's not 0, what is the order of the pole in this case? M, right? The order of the pole sometimes we call, instead of calling pole, we call singularity, or same of the singularity. Singularity in Korean is called 특이점. So actually name for pole, pole is like something like this, right? This is pole. So value of fc goes to infinite at that particular point. That's the reason why that point is called pole. Sometimes it is called singularity. The singularity and pole actually you can interchange the use. So I told you that in this case b1 can be calculated as m minus 1 factorial dz d z minus z naught to the m fc, and then you set z is equal to z0. This is a formula for calculating the residue. There are some simple methods to calculate when there is a simple pole. This is general formula. Pole of order m. If I like this color very much. This color is called sapphire blue. So there are different kind of blue. So for example, this is typical blue. This is blue, right? So a little bit different, right? The sapphire blue has a little bit of a violet plus. And sapphire is very expensive gemstone. sapphire, 그죠? 매우 비싼 보석이에요. If Z is a simple pole and Fz is of the form dz and z. This is called denominator, denominator. Denominator is 분자 and denominator is 분모. And usually this form is called a fraction. Fraction is 분수. So you learned 3 TOEIC words today, right? Actually 4. Singularity, nominator, denominator, fraction. Then the residue is simply T prime Z naught and Z naught. This proof is very simple. We know that Tz0 is equal to 0, right? Because it does have a pole. So this is you can say delta goes to 0 and Z naught plus delta T Z naught plus delta minus delta and D Z naught. You can actually, this is 0, right? You can always subtract 0 without changing anything. So this is basically, the denominator become what? Derivative. So it becomes T prime Z naught and Z naught. The proof is very simple. Another useful, we still time to copy. Oh, okay. Okay, so then so when f is analytic, then this particular formula is 2 pi I f Z naught. It does have a name called Cauchy's integral formula. And proof is not very difficult. Let's make a bit of a contour. So A, B. Let's call this is C1, C2, C0, C3. And maybe we call C prime as C1 plus C2, 0 plus C3. We have done this before, right? And the distance between this is called epsilon. So let's amplify this a bit. Then this part will C2, C3, and distance between this is epsilon. This is C naught. This is 0. So as epsilon goes to 0, what happens? C2 Z minus Z naught over FC dz C3. What happens if, let me see, I may have a pointer. Let's try to find out. Okay. C3 is going this way, right? C2. C3 is going the opposite direction. And if epsilon is going to 0, they are going to be just in the single line integral. Then this will be 0, right? So if epsilon goes to 0, C2 and C3 are opposite direction. So they're going to be 0, right? As C2 and C3 are in opposite direction. Also, as epsilon goes to 0, 0 what happens if epsilon goes to 0? Then this integral becomes closed contour, right? It becomes closed integral, but it's clockwise direction. Is actually opposite of counterclockwise. Right? If epsilon is going to 0, then this will be a closed circle, right? Circle, but this is a clockwise direction. But normally when we are dealing with this integral, it's supposed to control counterclockwise, so we change the sign. So we can continue this, but this is very important. But I think I have done this before in previous week. So same method. We now this integral. This is rho. By the way, this is 0. And at this point, z is rho exponential I theta. So counterclockwise, this is 0 to 2 pi rho exponential I theta f rho exponential I theta. Sorry, this is z minus here. OZ is z naught plus rho exponential I theta. So I have to change this into the following. Z naught plus rho exponential I theta. And this is actually, dz is rho exponential I theta, I d theta, right? So rho exponential I theta, I d theta. So this cancels each other. I 0 to 2 pi f c naught plus rho exponential I theta d theta. What happens if rho goes to 0? What happens? It becomes 2 pi I f c naught, right? So as epsilon goes to 0 and rho goes to 0, this integral two pi I f c naught. So can I continue? formed. And C prime is C1 plus C2, 0. Right? So what happens if we have C prime? Now, Z naught is outside, right? So now Fz, even including this denominator, is zonality inside of C1, right? C prime, sorry. C prime is C1 and this. So this point, particular point, is outside of this domain, right? So what happens? This Fg divided by Z naught, C minus Z naught is zonality, right? So it should be 0. Therefore, it should be 0. Then is equal to C1 minus closed 0 and C1 also become closed, right? As epsilon goes to 0 and C1 goes to C. It's equal to 0, right? Therefore, C if you set this epsilon goes to 0, then C1 becomes C, right? Because C2 and C3, if we sum over this, C2 and C3 is 0. So effectively, it becomes just C1 becomes C minus this. And this we just calculated. 2 pi I F C naught. So this proof the Cauchy's integral theorem, proof, formula. So maybe you can take a break for 5 minutes. Reshaping of this contour. No problem. No question. 이거 다 이해했어요? 어려울 것 같아서 이건 치팅이 좀 한국말로 다시 한번 설명해줄게요. 한국말 했다는 걸 얘기하면 안 돼요? 이 적분이 이런 D0가 있는 데에서 이 적분을 하려고 하는데 이렇게 한번 바꿔봤어. 안으로 들어가는 거 한 바퀴 돌고 다시 나가는 거 하고 밖으로 도는 거. 그 다음에 그 간격을 엡실론이라고 하고 엡실론이 0으로 가면 어떤 일이 생기겠어요? 일단 먼저 C2하고 C3는 방향이 반대지. 두 개 더하면 0이 되겠죠? 그죠? 그 다음에 요 적분도 엡실론 0으로 가면은 회곡면이 되잖아. 그죠? 회곡면인데 이쪽 방향은 시계 방향이 있는데 우리가 보통 생각하는 거는 시계 반대 방향이잖아. 시계 반대 방향으로 하면 부호가 바뀌겠죠. 그죠? 그 다음에 바뀌었죠. C와는 어떻게 되겠어요? 엡실론이 0으로 가게 되면 C와는 C가 되겠죠. 그죠? 그래서 C'에 대한 적분을 해버리고 나면 C'에서 봤을 때는 이 Z0가 밖에 있죠. 그죠? 도면이 밖에 있지. C'으로 이렇게 받쳐진 그 회곡면에 밖에 있으니까 전체 적분하면 어떻게 돼? 혹시 적분 정리에 의해서 0이 돼야지. 그죠? 0은 이제 얘랑 얘죠. 그죠? 얘는 아까 지난 앞장에서 계산하면 어떻게 돼요? 2파이 i의 ft 나스 잖아. 그러니까 결국은 이 적분은 이게 됩니다. 그래서 코에피시엔트를 formula가 정량이 됐어요. 그래서 어떻게 보면 수학은 잘 그리면 돼. 여러분들이 속된 말로 시험 볼 때 잘 못 보면 그렸다 그러지. 수학 시험 어떻게 봐서 그렸어 막그러잖아요. 근데 사실은 이게 반어법인데 그림을 잘 그리면 수학을 잘할 수 있어요. 여기까지. 한국말 한 건 녹음해버렸다. 내가 한국말 하지 말라고 했다는 것까지도 녹음해뒀네. 치밀하지 못했어요. 완전 범죄를 할 수 있었는데. 그래서 let's consider some example. Basic idea about complex integration is Cauchy in 18th century. He didn't have a computer, so he invented the method to calculate the complex integration using residue. So Cauchy's integral theorem and integral formula. So in this integral, actually we know the answer already. This is pi. y dx. Tangent inverse x. If we differentiate tangent inverse x, what do you have? 1 over x squared plus 1. You know this formula, right? So we already know that this answer, this I, dx d tangent inverse x dx tangent inverse x infinite to minus infinite pi over 2 minus pi over 2 is pi, right? We already know the answer. So what happens to this complex integration thing? So we consider the following integral. Fz has a pole, right? We have a right? So C1, C is equal to C1 plus CR. So what happens if we integrate C what do you have? We have only one pole, right? The residue F plus 1, right? I, sorry. This is I, this is minus I. Plus I. So the residue F I is what? Limit C I 1 over, you have 2C, right? So this is, you have NZ over DZ becomes T prime I and I, right? Using this formula, 2I. So this is 2 pi I 1 over 2I is pi. now. Okay, can I move on to the next slide? C1 C1 is actually on the rear axis, right? C1 rear axis. So it's actually minus L to R x squared plus 1 dx, right? How about CR? It's half circle, 0 to pi. So this is, say, R. This is R exponential I theta. R squared exponential I 2 theta plus 1. R exponential I theta. I d theta. Pi. So the absolute value of this integral is right. The absolute value of the integral is usually smaller than the integration of the absolute value, right? If you integrate into the absolute value, it's supposed to be smaller than, you take the absolute value first and then integrate. You probably learned in high school, and when denominator is smaller, it's bigger. So it's actually smaller than this pi r square right? When denominator is smaller, it's bigger. And it's actually so equal to 1 over r pi. So what happens as r goes to infinite? this integral less than 0, right? If this integration over the half circle is going to 0, right? And right? As r goes to infinite, it becomes minus infinite to infinite. This is what our original integral, right? So as r goes to infinite, this whole integration, c squared plus 1 dz is infinite to infinite dx plus cr pi. But we have seen that this goes to 0, right? So therefore, is pi. It's very interesting that pi is like a ratio between the radius, the diameter, and circumference. Right? Circumference is 1 circumference 1 diameter 지름. So pi is the ratio between the circumference and diameter of a circle, right? But how come this ratio is represented by some strange integral? And actually, we are going to see many cases that pi is a result of some complicated integration. So this is one good example of doing the complicated integral using complex integral, especially Cauchy's integral theorem. Any questions about this integral? This is a typical example of complex contour. This is called contour. We call this contour integration. It's a key part of a complex variable theory. So another example. Following integration. Bit over this integral is also related to Cauchy in 18th century, and it's related to some astronomical calculations between the planetary motion. Looks very complicated, right? Because we have a square root of. So Cauchy's idea is using this fz z to the 1/2 c squared plus 1. But if we have some problem, this particular function is not single valued. When z becomes z exponential 2 pi I, what happens? Z to the half is z to the half times exponential pi I is minus z to the 1/2, right? So we have to be really careful in choosing the contour. So we need the branch cut. So here we have C1, C2, 0, C3. And where are the poles? We have two poles, right? I minus I. Say this is R. C3 this integral is actually rho to the R x plus 1 x 1/2 dx, right? This is C1. Or C2, C3. How about C2? Here, this is, we have, at this point, this is x. This is x exponential I 2 pi I 2 pi. So C2, we have R to rho x exponential 2 pi I square plus 1 x exponential 2 pi I 1/2 dx, right? So this integral is just above x-axis. So you can say this is x, right? And this one square root of x and x squared plus 1. How about this integral? This integral is actually you circle 2 pi I. So this point is actually x times exponential 2 pi I. When you take a square root, what do you have? Minus, right? Exponential pi I. When you take a square root, exponential becomes exponential pi I, which is minus 1. So this is to rho x squared plus 1 minus square root of x dx, right? And becomes root 2r square root of x dx x squared plus 1. So therefore, C2 z squared plus 1 z 1/2 dz plus c3 z squared plus 1 dz become twice of root to r x squared plus 1 root to x dx. So this integral might be a little bit complicated, so I'm going to, okay, I'll turn. So there is no record that I explain this in Korean additionally to help you understand. So this is actually called branch cut. So branch cut is a very important concept in computer simplification because you like to do everything in a single valued way. So if you cross that x-axis, then it is no longer single valued. So this is CR, we have I minus I, C2, C rho, C3. So C is CR, C2 plus C3 plus C rho, right? The whole integration C CR C2 plus C3 is actually twice of root 2r x squared plus 1 root 2x dx, right? So this is actually our integral I plus 0 is 2 pi I residue I is exponential I pi over 2 exponential I 3 pi over 2 residue f pi over 2 exponential I residue f exponential I 3 pi over 2. So let's calculate. It's going to be 0 as r goes to infinite. I as rho goes to 0, r goes to infinite. This is going to 0 as rho goes to 0. So we are going to show this later. But we will calculate this residue first. So this integral is very useful. So let's calculate the residue first. Can I move on to the next page? So we have so 2I z to the 1/2 z squared plus 1. This is nz over dz, right? So residue f exponential I pi over 2 is actually twice of exponential I pi over 2, right? And this is exponential I pi over 4. So 2I and cosine pi over 2 plus I sine pi over 2. 4 is 1 over 2I How about this? Residue of exponential I 3 pi over 2 is exponential I 3 pi over 4 to exponential I 3 pi over 2 is minus 2I cosine 3 pi over 4 I sine 3 pi over 4. So let's say or sine, tan, cosine, right? So cosine 3 pi over 4 is minus 2I minus square root of 2, right? Plus I square root of 2. Probably you remember the Olsa Tanko in freshman in high school, right? Everything is positive, sine is positive, tangent is positive, cosine is positive. So pi over 4 is in this area, in this region. So sine is positive. If you add them together, what happens? So residue f exponential I pi over 2, residue f exponential I 3 pi over 2 is actually 2I over square root of over 2, right? So 1 over I square root of over 2, 2. Therefore, 2 pi I times residue f exponential I pi over 2, residue f exponential 3 I pi over 2 is 2 pi I times 2I square root of 2 we have 2I. 2I, right? We have 2. So pi over square root of 2, 2. Oh. So let's go back to the original. Or I is pi over square root. That means again you have pi. I haven't shown two integrals which is going to be 0, right? So I'm going to do that. If CR and 0 integrals vanish. So let's do, how about this CR? So CR integration is this. Zero to 2 pi. 0 to 2 pi r square exponential I 2 pi plus 1 r half exponential I theta over half I r exponential I theta d theta, right? Is less than absolute integral r square exponential I 2 pi plus 1 r half exponential I theta over 2 I r exponential I theta d theta is less than actually r to the half over 2 pi goes to 0 as r goes to infinity, right? Another integral. Am I going too fast? So it looks like one integral take about half an hour. Let me see. This I 2 theta. 2 theta. Now this integral. This is rho. 0 minus 0 to 2 pi rho square exponential I 2 pi plus 1 rho 1 half exponential I theta over 2 rho exponential I theta I t theta, right? Minus rho to the 2 over 3. The integration is over theta, so rho can be put out. Rho square 2 theta exponential I 2 theta plus 1 exponential I 3 theta over 2 I t theta. What happens as rho goes to 0, this will goes to 0, right? So front factor goes to 0, so this integral becomes 0. So we know that as rho goes to 0, this 0, z square plus 1, z to the 1 half dz goes to 0. Therefore, we have this integration 0 to infinite x squared plus 1 root x dx is pi over square root of 2. So again, we have pi. Strange, right? So this has something to do with the curvature of this universe. So in flat space-time, the ratio between diameter and circumference is pi. So we are living in this universe such that the ratio between diameter and circumference is pi. That's the reason why I want this integral equal to pi. If somehow some supernatural thing created our universe in different way, slightly different from pi, then this integral may not be no longer pi. So this has something to do with the current curvature of space-time here. Because you may be hungry, so I'd like to stop here today. What do you think? So we can continue next week. This very interesting complex integration next week.